Time feels simple when we're living inside it. You wake up, a day passes, another memory settles quietly into the past, and no matter how much you want to hold on to a moment, it never comes back. We grow older without noticing the exact instant it happens. One day blends into the next, and it feels natural to believe that time is a river, always flowing forward, carrying everyone along at the same steady pace. But modern physics tells a very different story. According to our best understanding of the universe, time does not flow at all. It can slow down, it can stretch, and under the right conditions, two people can live through the same day and age by different amounts. That may sound like science fiction, but it isn't. In fact, something remarkably close to time travel has already happened, quietly, without a machine, and without changing the world overnight. Somewhere above your head, astronauts have experienced time differently than the rest of us, not by imagination, not by illusion, but because the universe itself allowed it. Tonight, we're going to explore how that's possible, how traveling into the future has already occurred in small but measurable ways, why traveling into the past is far more complicated, and where the equations of Einstein reveal subtle cracks, tiny openings, inside time itself. It's how much of it the universe already allows. To understand how time travel becomes possible at all, we first have to face an uncomfortable truth. Time isn't what it feels like. At first, time feels simple. It's what clocks measure. It's what calendars organize. We wake up in the morning, move through the day, and fall asleep at night, guided by numbers on a screen or hands on a dial. We remember what came before. We plan for what comes next. And without thinking too much about it, we assume time moves forward in the same way for everyone. That assumption feels natural. But it turns out to be wrong, because everything we just described, clocks, calendars, schedules, are tools. They help us stay organized, they help society function. But they are not the same thing as time itself. Physics discovered this the moment it started asking deeper questions. There is no master clock somewhere in the universe, ticking away for everything that exists. No single reference point that tells all galaxies, stars, and planets what time it is right now. In fact, there may not even be a shared now. That idea is uncomfortable because our experience depends on it. We feel like the present moment should be universal. But once distance becomes large enough, even that breaks down. Two people, far apart in space, can honestly disagree about what now means, and both of them can be correct. Not because anyone is confused, not because time is malfunctioning, but because information itself takes time to travel. In everyday life, this doesn't seem to matter. Your coffee still cools. The sun still rises and sets. A minute still feels like a minute. But the universe isn't obligated to match what time feels like inside a human mind. And this is where our old intuition begins to loosen. Modern physics doesn't treat time as something that exists on its own, flowing independently through the universe. It discovered something far stranger. Time is deeply connected to space itself. So deeply, in fact, that you can't fully describe one without the other. They form a single structure, not time and space, but space-time. And once time and space stop being separate things, the rules we rely on, about order, motion, and change, start to bend in ways that feel unfamiliar. This isn't where the story becomes confusing, it's where it finally starts to make sense. For a long time, the universe seemed simple. Space felt solid and unmoving. Time felt steady, ticking forward at the same pace for everyone. And gravity was thought of as a force, something that reached out and pulled objects together. That picture worked, until Einstein changed it. He showed us something unexpected. Space is not rigid, and time does not exist on its own. They are part of a single structure, and that structure can change. To understand this, imagine the universe not as a solid stage, but as something closer to a surface. When nothing is there, the surface stays flat. When something massive appears, like a planet or a star, the surface changes shape. Objects don't move because they're being pulled. They move because the universe around them isn't shaped evenly. A planet doesn't fall toward a star because a force grabs it. It moves the way it does because space near the star is different from space farther away. The planet simply follows the easiest path through that shape. This is what gravity really is. Gravity isn't a force pulling you down. It's the shape of the universe guiding motion. And here's the part that matters most for time. Time is part of that same structure. It isn't layered on top of space. It isn't separate from it. It's built into the universe itself. So when space changes shape, time changes with it. Where the universe bends more deeply, time slows down. Not as a feeling, not as an illusion, but in a way that clocks can measure. Two identical clocks placed in different locations will not always agree. One will quietly fall behind the other, simply because of where it is. This is the moment time stops being just something we experience. It becomes physical. Something shaped by mass. Something affected by the universe around it. And once time becomes physical, it can no longer behave the same everywhere. The universe isn't flat. And because of that, time isn't steady. This is where time travel first leaves science fiction, not through machines, but through the simple fact that time itself can slow down. Up to this point, time has already lost some of its certainty. It can slow down, it can stretch, and it doesn't behave the same everywhere. But modern physics goes one step further, into territory that feels genuinely unsettling. In the mathematics of relativity, time is treated the same way as space, not as something that moves, but as a coordinate, a location. Just like here or there, time becomes a matter of when. And once you look at it that way, a strange idea emerges. What if time doesn't flow at all? This is where physicists talk about something called the block universe. The name sounds technical, but the idea itself is simple. Imagine a book that has already been printed from beginning to end. Every page exists at once. The first page, the last page, and every page in between. When you read the book, it feels like the story is unfolding, page after page, moment after moment. But the story itself isn't being created as you read it. It already exists. You're just moving through it. According to this view, the universe may work the same way. The past hasn't vanished. The future hasn't been created yet. Both may already exist, just as real as the present moment you're experiencing now. In the equations, there is no special marker for now. No highlighted line separating past from future. Physics doesn't recognize a privileged present moment. That can feel deeply uncomfortable. Our entire experience depends on the idea that time is moving forward. We remember the past. We plan for the future. We feel ourselves traveling through time, carried along by something we can't stop. But the universe itself may not share that experience. This doesn't mean your life is an illusion. It doesn't mean moments don't matter. It means that the feeling of time flowing may be something that emerges from how human minds experience reality, not something built into the universe itself. And this is where the real question appears. If every moment exists, if the universe isn't moving from past to future the way we feel it is, why does life feel so one way? Why do memories only point backward? Why does a broken cup never reassemble itself? Why do we age in one direction without exception? The equations stay silent on that question. They describe what exists, but not how it feels to live inside it. And so, just as time stops behaving the way we expect, we're forced to look elsewhere for the answer. Not in space-time itself, but in something far more familiar. Something quietly at work in every ordinary moment of life. That's where the direction of time truly begins to appear. If every moment exists, why does life still feel like it only moves in one direction? That was the question we left hanging. Because in a block universe, the past and the future may both be real. The equations don't draw a bright line called now, and yet your experience is nothing like that. You remember yesterday. You don't remember tomorrow. You can plan for the future, but you can't visit it. And once something happens, it stays happened. The simplest way to see this is in ordinary quiet things. Drop a glass on the floor and it shatters. It never gathers itself back together. A room gets messy all by itself. It doesn't clean itself while you're not looking. Life seems to lean in one direction. Physics has a name for that direction: entropy. Entropy is often described as disorder, but you don't have to think of it as chaos. A simpler way to picture it is this: entropy is what happens when things spread out, when energy and matter move from neat and concentrated to mixed and scattered, and the universe has a strong preference for that direction. This is the heart of the second law of thermodynamics. In a closed system, entropy tends to increase, not because the universe is trying to be messy. There's no intention behind it. It's because there are vastly more ways for things to be mixed up than there are for them to be perfectly arranged. A shattered glass can exist in millions of scattered patterns across the floor, but there are only a few ways for it to be whole. So the whole glass is rare. The broken glass is common. That simple imbalance creates something profound. As entropy increases, it creates a difference between before and after, a direction you can point to. And that direction is what we call the arrow of time. This is why the past feels fixed. It's the direction in which entropy was lower. And the future feels open because it's the direction in which entropy can still increase. Even memory is tied to this. Your brain records information by changing physical states, tiny arrangements of molecules and energy. Those changes leave traces. They require energy. They produce heat. They increase entropy. Memory works because it leaves a footprint in the physical world, and that footprint only forms in one direction. So, the arrow of time doesn't come from time itself. It comes from the way the universe changes, from the statistical fact that order is fragile and mixing is easy. And once you understand that, something else becomes possible. If the flow of time is really a result of entropy, then the next question isn't philosophical, it's almost dangerous. What if entropy could be locally cheated? What if, under the right conditions, the universe could create a pocket where time doesn't behave the way it usually does? And once we understand why time feels one way, we can finally ask a dangerous question. Can that direction ever be bent? Up to now, the direction of time has felt universal. Entropy explains why life moves one way, why memories point backward, why the future feels open and the past feels fixed. And for most everyday situations, that picture works. But Einstein discovered something unexpected. Even though entropy creates a shared sense of time, the universe does not require time to move at the same rate for everyone. In other words, the clock you carry through life is not guaranteed to match someone else's. This is where the first real crack appears. Physics calls it time dilation. The idea is simple, even if the consequences are strange. Time does not pass equally for all observers. Two people can experience different amounts of time, even while living through the same events. Imagine two identical clocks, two identical people. They start together. Then one of them leaves, moving faster or entering a region where gravity is stronger. Later, they reunite. Nothing dramatic happens in the moment. No alarms, no flashes of light. But when the clocks are compared, they no longer agree. One has fallen behind the other. This isn't a thought experiment. It isn't a metaphor. It isn't philosophy. It has been measured. Time dilation is a direct prediction of Einstein's relativity, and it shows up in the real world. The faster you move through space, the more slowly your time passes. The deeper you are in a gravitational field, the more time slows down around you. The differences are usually tiny. So small you'd never notice them in daily life. But they are real. And once you accept that, something important changes. Time stops being a single, universal background that everyone shares. It becomes personal, local, dependent on where you are and how you move through the universe. Two clocks can honestly disagree, and neither one is wrong. This is the moment when time travel stops sounding like pure science fiction. Not because anyone is jumping through centuries, not because the past is being rewritten, but because the future has already become uneven. Some paths through the universe carry you forward faster than others. And as strange as that sounds, it's not just a theoretical possibility. It has already happened to real people. Quietly, without headlines, and without anyone realizing it at the time. One of them spent years orbiting the Earth, and when he finally came home, he had done something remarkable. He had arrived from the future. His name is Sergei Krikalev. He isn't a scientist in a lab. He isn't a theorist with equations on a chalkboard. He's a cosmonaut. Over the course of his career, Krikalev spent more time in space than almost anyone alive. More than 803 days orbiting the Earth. Months turned into years as he circled the planet again and again, living aboard space stations that never truly stopped moving. To understand what that means, picture his daily routine. The International Space Station doesn't hover above Earth, it races around it. One full orbit takes about 90 minutes. That means the station circles the planet roughly 16 times every day. While doing so, it travels at a speed of about 7.66 kilometers per second, more than 27,000 kilometers per hour. That speed is the key. According to Einstein's relativity, motion affects time. The faster you move through space, the more slowly your time passes compared to someone who stays behind. This effect is incredibly small at everyday speeds. You don't notice it in a car, you don't notice it on a plane. But at orbital speeds, it becomes real. Every single lap around Earth, the clocks aboard the station tick just a little more slowly than clocks on the ground. Not by seconds, not by milliseconds you can feel. By fractions so tiny they seem almost meaningless. Almost. Because Krikalev didn't make one orbit, he made thousands. Those tiny differences added up, day after day, month after month, year after year. And when scientists compared the numbers, they found something remarkable. When Sergei Krikalev finally returned to Earth, his body had experienced about 20 milliseconds less time than the planet he left behind. He was, in a precise and measurable way, slightly younger than everyone who stayed on Earth. Not by enough to see in a mirror, not by enough to change his life, but enough to matter. This wasn't a prediction, it wasn't a simulation, it wasn't a clever story, it was a measurement. No machine carried him forward, no portal opened, no laws of physics were broken. Time simply treated him differently because of where he was and how fast he was moving. That's what makes this moment so important. Time travel didn't arrive with flashing lights or paradoxes. It arrived quietly, hidden inside the normal operation of the universe. Inside speed, inside motion, inside the geometry of space-time itself. Krikalev didn't jump centuries into the future, but he did cross a line. He proved that time does not belong equally to everyone. Two people can begin together, live separate paths, and reunite having aged by different amounts. The difference may be small, but the meaning is enormous. Because once something is possible in a small way, physics doesn't treat it as a novelty. It treats it as a hint, a sign that the same rules could apply on larger scales under more extreme conditions. Krikalev's journey shows us something quietly profound. The future is not sealed off. It isn't unreachable. It isn't reserved for fiction. It's already accessible, fraction by fraction, along certain paths through the universe. And his story wasn't an exception. It was a preview. What happened to him in milliseconds could, in principle, happen by seconds, minutes, or far more if the conditions were right. Which brings us to the next question. If motion can carry you into the future, what happens when speed itself approaches its ultimate limit? By now, the idea should feel unfamiliar, but no longer impossible. Time doesn't pass the same way for everyone. It depends on where you are, and it depends on how you move. This is the core of time dilation. In Einstein's universe, time is not something you carry with you unchanged. It responds to motion. The faster you move through space, the more slowly your time passes compared to someone who remains still. This isn't about perception. It isn't about feeling rushed or relaxed. It's not psychological. It's physical. A helpful way to picture it is something very ordinary. Imagine watching a movie in slow motion. To you, everything looks normal. You don't feel slowed down. Your thoughts move at the same pace. But when someone else watches that same scene at regular speed, they see something different. Movements stretch out, actions take longer. Time dilation works like that, but with reality itself. From your point of view, nothing feels unusual. Your heartbeat feels normal. Your thoughts feel normal. Your day unfolds the way it always has. But to someone watching from a different frame of motion, your clock is running slow. And this isn't an idea left floating in theory. We've measured it. Scientists have taken extremely precise atomic clocks, accurate to billionths of a second, and flown them around the Earth. Some clocks stayed on the ground. Others were placed on aircraft or satellites, moving rapidly through space. When the clocks were brought back together and compared, they disagreed. The clocks that traveled returned slightly behind, not because they malfunctioned, not because of error, but because motion changed the amount of time they experienced. These experiments have been repeated again and again, with planes, with satellites, with spacecraft. Every time, the result is the same. The faster the clock moves, the more slowly it ticks. And the relationship isn't linear. It's not gentle. As speed increases, the effect grows stronger. At everyday speeds, the difference is too small to notice. At orbital speeds, it becomes measurable. And as you push closer and closer to the speed of light, time itself begins to behave in ways that break our intuition. This is where something profound happens. Motion doesn't just move you through space, it changes how you move through time. Two people can start together. One stays behind, the other travels fast. When they reunite, they are no longer the same age, not because time was distorted subjectively, but because the universe kept track of their paths differently. This is why time dilation isn't an illusion. It's written into the structure of space-time. And once you accept that, a quiet realization follows. Time is negotiable. Not in the sense that you can choose it freely, not in the sense that you can reverse it at will, but in the sense that the universe allows different rates of time to exist at the same moment. This doesn't violate causality. It doesn't undo the arrow of time. Entropy still increases. Memory still points backward. But within those boundaries, time becomes flexible. You don't need a machine to experience this. You don't need exotic physics. All you need is motion. And that raises an unavoidable question. If modest speeds already slow time by tiny, measurable amounts, what happens when speed itself approaches its ultimate limit? What happens when motion pushes against the fastest thing the universe allows? Because there is a limit, a hard boundary woven into space-time itself, and near that boundary, time no longer behaves gently. It begins to stretch, it begins to separate, and the future starts pulling away from the present in ways that feel almost unreal. And when speed approaches its ultimate limit, time begins to behave in ways that feel almost unreal. By now, the rule should be clear. The faster you move, the more slowly time passes. At everyday speeds, the effect is tiny. At orbital speeds, it becomes measurable. But when motion begins to approach the speed of light, time dilation stops being subtle. It becomes overwhelming. Imagine a spacecraft traveling not just fast, but extremely fast. So fast that it's moving at a significant fraction of the speed of light. Inside the ship, everything feels normal. Days pass, meals are eaten, sleep comes and goes. 1 year of life unfolds exactly the way a year always does. But far away, on Earth, something very different is happening. Clocks there are racing ahead. For the people who stayed behind, that single year aboard the ship might correspond to decades on Earth. Entire generations could pass. Cities could change. Technology could evolve. The world could quietly move on. And no one would be wrong. A useful way to picture this is something simple. Two people sit down to watch the same movie. One watches it at normal speed. The other watches it in slow motion. From each person's point of view, the movie makes perfect sense. Every scene plays smoothly. Every moment follows naturally from the last. But when they compare notes afterward, they've experienced completely different amounts of time. That's what near-light speed does to reality. From the traveler's perspective, nothing feels delayed. Their heart doesn't slow. Their thoughts don't stretch out. Life proceeds normally. But when they return, if they return, they arrive in a future that has moved far beyond them. This isn't because time is being fooled, it's because time is doing exactly what the universe allows. No laws are broken, no paradoxes are created. The traveler hasn't gone backward, they haven't escaped causality. They've simply taken a path through space-time where less time was required. In that sense, traveling into the future doesn't require exotic machines or forbidden physics. It requires only one thing: extreme motion. And the closer that motion gets to the speed of light, the more dramatic the effect becomes. In principle, someone could leave Earth, spend a few years traveling at near light speed, and return to find a world that barely remembers who they were. Not because they were lost, but because time treated them differently. This is what gives time travel its strange asymmetry. You don't need to go backward to lose everything you know. You only need to go forward fast enough. Time doesn't resist the future. It allows it, unevenly. And speed, as powerful as it is, isn't the only thing that can stretch time. There's another influence, equally real and far more common: gravity. So far, we've seen how motion can stretch time. Move fast enough, and your clock falls behind. Take a different path through space-time, and the future opens unevenly. But speed isn't the only thing that affects time. Gravity does too. Earlier, we learned that gravity isn't a force pulling objects inward. It's the shape of space-time itself. Massive objects change that shape. They make space-time curve more deeply around them. And when space-time bends, time bends with it. This leads to a simple but unsettling consequence. The stronger the gravity, the more slowly time passes. Near something very massive, time runs behind compared to places where gravity is weaker. Not as a feeling, not as a metaphor, but in a way that can be measured. This idea feels dramatic when we imagine extreme objects. Think about a region close to a black hole. Gravity there is so intense that space-time curves sharply. In such an environment, hours experienced near the black hole could correspond to years far away, where gravity is weaker. That image may feel familiar from movies, especially scenes where characters return to find the world far older than they expected. What matters here isn't the drama. It's that the effect itself is real. The mathematics behind those scenes isn't invented for storytelling. It comes directly from Einstein's equations. The idea that gravity slows time isn't science fiction. It's a natural prediction of how space-time behaves. But we don't need black holes to see this. Gravity changes time even here on Earth. Scientists have tested this using atomic clocks so precise they can detect differences smaller than a billionth of a second. Two identical clocks are synchronized. One is kept closer to Earth's surface, where gravity is slightly stronger. The other is placed higher, on a mountain or aboard a satellite, where gravity is weaker. They are left to run. When the clocks are brought back together, they no longer agree. The clock that spent time higher up has ticked a little faster. The clock closer to Earth has fallen behind. The difference is tiny, but it's real. Time has passed at different rates, simply because gravity was different. This means something remarkable. Time is already uneven across the planet. It moves a little more slowly at sea level than it does on a mountain peak. It moves a little more slowly at your feet than it does at your head. The effect is small, but it's there, woven into the fabric of everyday life. You don't feel it, you don't notice it, but the universe does. And this brings the idea of time travel closer than most people realize. You don't need to leave Earth to experience different rates of time. You don't need to approach the speed of light. Gravity alone is enough. This doesn't mean we can jump centuries ahead by climbing a mountain. The differences are far too small for that. But the principle is what matters. Time responds to mass. It slows down near heavy objects. It speeds up where gravity weakens. Once again, clocks can honestly disagree, and neither one is wrong. They are simply embedded in different parts of space-time. This is why time travel into the future doesn't require breaking the universe. It doesn't require loopholes or violations. It follows directly from the same rules that govern falling objects and orbiting planets. Gravity doesn't just bend space, it bends time. And if space-time can be bent naturally, by mass and motion, then the next question becomes unavoidable. Is this bending something the universe only allows to happen? Or something that could, in principle, be shaped deliberately? Up to now, every form of time travel we've discussed has followed a familiar rule. You move through space, and time responds. You go fast, time slows down. You approach massive objects, time stretches. But all of those ideas still imagine a ship fighting its way through the universe, pushing harder, accelerating faster, struggling against limits. Then, in the 1990s, a very different idea appeared. What if you didn't move through space-time at all? What if you moved with it? This is the idea behind what's known as a warp bubble. The concept comes from a solution to Einstein's equations proposed by physicist Miguel Alcubierre. It doesn't describe a rocket engine, it doesn't describe thrust, and it doesn't ask a ship to break the speed of light. Instead, it changes the shape of space-time itself. Here's the core idea, stripped of math. Imagine space-time as something flexible. If you could gently squeeze it in front of a spacecraft and gently stretch it behind, you wouldn't need to push the ship forward at all. The space in front would shrink, the space behind would expand, and the region containing the ship would ride along inside that distortion. The ship wouldn't be racing through space. Space would be moving. Inside this bubble, the spacecraft would be essentially at rest. No extreme acceleration, no crushing forces, no relativistic limits being violated locally. From the crew's point of view, nothing dramatic would be happening at all. And yet, from the outside, the bubble could move faster than light relative to distant observers. Not because the ship itself breaks the cosmic speed limit, but because the universe around it is doing the moving. This is what makes the idea so unsettling. Einstein's equations don't forbid it. They don't say this kind of space-time distortion is impossible. They simply describe what it would take, and if such a bubble could exist, the consequences for time would be extraordinary. Inside the warp bubble, time would pass normally for the crew. Days would feel like days, years would feel like years. But outside the bubble, across the stretched and compressed space-time, far more time could pass. A journey that feels short to the traveler could span decades, or even centuries, for the rest of the universe. Not because time is being tricked, but because space-time itself is being reshaped. This places warp bubbles in a strange category. They aren't traditional time machines. They don't reverse cause and effect. They don't send messages into the past. But they could, in principle, carry someone far into the future, without them experiencing the passage of that time. So, why aren't we doing this already? Because the price is enormous. To create a warp bubble, the equations require something unusual: negative energy density, a form of energy that behaves opposite to anything we normally encounter, something often referred to as exotic matter. This isn't imaginary, but it's rare. In quantum physics, there are small, fleeting examples where energy behaves this way. One of them is known as the Casimir effect, where two closely spaced surfaces can create a tiny region of negative energy due to quantum fluctuations. The effect is real. It has been measured, but it's incredibly small. To build a warp bubble large enough for a spacecraft, you'd need amounts of exotic energy far beyond anything we know how to produce or control. That's where modern research enters the picture. Physicists and engineers, some working with space agencies, have explored whether the original requirements could be reduced, whether the shape of the bubble could be adjusted, whether the energy demands could be softened. At NASA's Eagle Works laboratory, researchers examined modified versions of the warp concept, looking for configurations that might bring it closer to physical plausibility, not as a blueprint, but as an exploration. The conclusion remains cautious. Warp bubbles are not currently achievable. They may remain beyond our reach for centuries, or they may never be built at all. But the important point is this: they are not ruled out by the laws of physics. The equations don't close the door. They leave it slightly open, and that alone is remarkable, because it suggests something profound about the universe we inhabit. Space-time may be more flexible than we ever imagined, not just bent by stars and planets, but, in principle, shaped deliberately. Whether humanity ever learns to do that is an open question. But the fact that the mathematics allows it tells us something quiet and powerful. The future is not sealed shut, and warp bubbles aren't the only strange doorways hidden in the equations. Black holes are familiar by now. They pull everything inward. Matter, light, even time itself falls past a boundary it can never escape. But the equations that describe black holes contain a strange mirror image, an idea that feels almost backward. Physicists call it a white hole. In theory, a white hole is the opposite of a black hole. Instead of pulling things in, it only pushes things out. Nothing can enter it. Matter and energy can emerge, but never return. If a black hole is a cosmic trapdoor, a white hole would be a cosmic exit. This isn't something anyone has observed directly. No telescope has confirmed the existence of a white hole. No experiment has detected one. For now, they remain mathematical objects, solutions that appear naturally when the equations of general relativity are extended and reversed. And yet, the fact that they appear at all is unsettling, because the mathematics doesn't dismiss them as nonsense. It allows them. If white holes exist, they would be regions where space-time is curved in an extreme and unusual way, a place where matter is expelled, not absorbed, a place that behaves unlike anything we see in ordinary astrophysics. And this is where time enters the story again. Inside such extreme curvature, time would not behave normally. The paths through space-time could twist and stretch in ways we don't fully understand. An object passing through that region might experience time very differently from the rest of the universe. One possibility, still speculative but consistent with the equations, is that a white hole could act as a kind of one-way time passage. Something could enter a region of distorted space-time and emerge far into the future. Not because time was reversed, not because causality was broken, but because the journey through space-time itself required very little time for the traveler, while the outside universe moved on. And once something emerges from a white hole, there is no going back. That's the defining feature. No return path, no second crossing, no undoing the journey. In that sense, white holes wouldn't be time machines in the way fiction imagines them. They wouldn't allow revisiting the past. They wouldn't create loops or paradoxes. They would allow only one thing: forward travel. A door that opens once and never again. This makes them fundamentally different from warp bubbles or near light speed travel. Those ideas stretch time, but they still allow return. A traveler could come back and find the world changed, but still accessible. White holes, if they exist, would offer no such comfort. They would represent the ultimate one-way journey. And that's why they sit at the edge of modern physics. There's no evidence that nature actually builds them. Some physicists believe they may be unstable or impossible to form under realistic conditions. Others wonder whether they might be connected to black holes in ways we don't yet understand. For now, they remain on the boundary between mathematics and reality. But even as an idea, they tell us something important. They remind us that the universe may contain structures that don't fit neatly into our intuitions about time. Paths that move only forward. Doors that open once and never close. And that leads to an even more unsettling question. If the universe allows one-way journeys forward, is there any path, any structure, any loophole at all that could ever allow a return? Because if moving into the future is already possible, then the real mystery isn't how to go forward. It's whether the past is truly sealed, or simply hidden behind a barrier we haven't learned how to cross yet. Up to now, every form of time travel we've explored has involved the universe itself. Space-time bends, time stretches, motion and gravity do the work. But there is another idea, far quieter, far more personal, that doesn't ask the universe to change at all. What if you don't move through time, and instead, you simply stop? If you can't carry the universe forward with you, could you pause your own biological clock and let the future come to you? This is the idea behind cryonics. Cryonics is not science fiction hibernation. It isn't suspended animation from a movie. It's a form of biological preservation. The process begins after legal death, when the heart has stopped and the brain is no longer receiving oxygen. The body is rapidly cooled and preserved at extremely low temperatures, around -196 degrees Celsius, using liquid nitrogen. At those temperatures, chemical reactions slow almost to a halt. The processes that normally cause cells to break down over time are dramatically reduced. The goal is not revival today. The goal is preservation. Cryonics operates on a simple bet that future medicine may be able to repair damage that today's technology cannot. That what is irreversible now might not remain irreversible forever. This idea isn't new. The first person to undergo cryonic preservation was James Bedford in 1967. His body has been maintained in cryogenic storage for decades. He has not been revived. No one has. That fact matters. Cryonics has never successfully brought a human back to life. There is no proof that it ever will. Anyone who chooses it is accepting uncertainty at the deepest level. And yet, the physics behind it is straightforward. Lower temperatures slow chemistry. Slower chemistry means slower decay. And slower decay means time, biologically speaking, is passing at a dramatically reduced rate. From the preserved person's point of view, if revival were ever possible, very little time would pass at all. Conscious experience would stop. Decades or centuries could move by without being felt. In that sense, cryonics is a kind of time travel, not backward, not even forward in the usual way. It's a leap over time. A person preserved today might awaken in a world profoundly changed, technologies unrecognizable, cultures transformed, everyone they once knew long gone. The cost of skipping time would be loneliness. This is where cryonics becomes less about physics and more about choice. It doesn't conquer time, it doesn't bend space-time, it doesn't cheat entropy, it simply waits. And waiting carries its own risks. There is no guarantee of success, no promise of awakening, no assurance that the future would even want to bring someone back. Cryonics asks a deeply human question. Is it better to accept the finality of your own time, or to gamble on a future you may never see? Some people find hope in that question, others find discomfort. But either way, it reveals something important about how we think about time travel. Not every path forward requires advanced physics or cosmic engineering. Some paths depend only on biology, technology, and personal willingness to let go of the present. Cryonics doesn't claim to defeat time. It accepts time's power and steps aside, hoping it will pass overhead. But waiting for the future is very different from trying to return to the past. And that difference leads us into the most dangerous territory of all. Because if moving forward is possible in many ways, the real mystery is whether backward travel, true return, can ever exist at all. For most people, time travel means one thing: going back. Popular culture has trained us to imagine the past as something flexible, something that can be edited. In stories, a single change can ripple forward, rewriting entire timelines. Fix one mistake, and the present transforms. Make one wrong move, and everything collapses. It's a powerful idea, and it feels intuitive. But physics is far less forgiving. From a scientific point of view, the past isn't a memory or a story. It's a set of events that have already happened. In the language of relativity, each of those events occupies a specific location in space-time, a when just as real as a where. And that's where the trouble begins. Because once events are fixed in space-time, moving backward isn't just a matter of travel, it's a challenge to causality itself. Causality is the quiet rule that underlies everything we experience. Causes come before effects. Actions lead to consequences. The universe depends on that order to make sense at all. When you imagine traveling to the past, you're not just visiting an earlier moment. You're inserting new causes into a chain that has already produced its effects. That's what creates paradox. The most famous example is often called the grandfather paradox. The idea is usually dramatized, but it doesn't need drama to be troubling. If someone travels to the past and prevents a key event from happening, they risk erasing the very conditions that allowed them to travel in the first place. But the deeper problem isn't violence or dramatic interference. it's information. Even sending a single piece of information backward, one warning, one message, one altered decision, can be enough to unravel cause and effect. If the future can influence the past, then the past is no longer stable. And if the past isn't stable, the present loses its foundation. This is why backward time travel is so much more dangerous than moving forward. Traveling into the future doesn't disturb causality. It simply skips ahead along an existing path. But traveling into the past asks the universe to tolerate loops, situations where an event can be both the cause and the result of itself. Physics does not like loops. Some stories try to soften this by imagining self-consistent timelines, where whatever you do in the past was always part of history. No changes, no contradictions. Everything happens exactly as it already did. But even this idea raises uncomfortable questions. If nothing can be changed, then what does it mean to go back at all? And if something can be changed, how does the universe prevent logical collapse? Films sometimes gesture toward answers. In Interstellar, Cooper doesn't return to the past in a physical sense. He doesn't step into an earlier moment and walk around. Instead, he influences the past only through information, through gravity, through subtle signals. Even there, the story treats backward influence as something fragile and constrained, a narrow channel, a last resort. That restraint reflects a deeper truth. Every attempt to move backward through time runs into the same wall. The universe appears structured to protect causality, not actively, not deliberately, but through the way its laws fit together. The past isn't guarded by force fields or cosmic rules written in bold letters. It's protected by consistency, by the fact that once effects exist, their causes must already be settled. This is why backward time travel remains the most controversial idea in all of physics. Not because it's dramatic, but because it threatens coherence. And yet, the story doesn't end there. Because buried inside Einstein's equations, deep in the mathematics that describe space-time itself, are strange solutions. Narrow paths, extreme geometries, possibilities that don't behave the way space-time usually does. They don't offer easy returns. They don't promise safe changes. But they suggest that under the right conditions, time might not be strictly one way everywhere. If such paths exist, they wouldn't look like movie time machines. They wouldn't allow casual visits to the past. And they wouldn't tolerate paradox. They would be rare, unstable, and tightly constrained. Yet their very existence forces us to confront an unsettling idea. Maybe the past resists us not because it's impossible to reach, but because reaching it requires space-time to twist into shapes the universe almost never allows. And that brings us to the next question. If backward travel is even theoretically possible, what kind of structure could bend space-time enough to let time loop back on itself? Because if such structures exist, they would be unlike anything we encounter in everyday reality. They would be hidden at the very edges of physics. Yet, inside Einstein's equations, there may be narrow paths that loop through time itself. If the past resists us, it's not because physics has never imagined a way back. It's because the ways back, if they exist at all, sit at the edge of everything we understand. One of the most famous is the wormhole. A wormhole is often described as a shortcut through space-time, not a tunnel carved through normal space, but a connection between two distant regions of the universe created by space-time itself. The easiest way to picture it is simple. Imagine the universe as a sheet of paper. 2 points can be far apart on that sheet. To travel from one to the other, you'd have to move across the surface, mile after mile, year after year. But if you fold the paper so those 2 points touch, something changes. Now the distance between them is almost nothing. Punch a hole through the folded sheet, and you've created a path that bypasses the long route entirely. That's the idea of a wormhole. It connects two locations that would otherwise be separated by vast distances. From the outside, it looks impossible. From the inside, it could be a short passage, one step through a throat of curved space-time, and you emerge somewhere else. This isn't pure fantasy. Wormholes appear as real mathematical solutions within general relativity. The equations allow them. They don't guarantee nature creates them, but they don't forbid them either, and that alone makes them worth taking seriously. But there's a catch. A wormhole that collapses instantly would be useless. If you try to pass through it, it closes before anything can cross. To keep a wormhole open, the equations suggest you need something extremely unusual. Negative energy, exotic matter. Just like the warp bubble, stable wormholes seem to require a kind of energy density that behaves opposite to ordinary matter. Something that can hold space-time open rather than letting it pinch shut. We have small hints of negative energy in quantum physics, but nothing remotely close to the scale a traversable wormhole would require. So already, we're standing in speculative territory. But even if we set that problem aside and imagine a stable wormhole exists, something even stranger follows. A shortcut through space can become a shortcut through time. Here's how. A wormhole has two openings, often called two mouths. One mouth could be near Earth. The other could be far away, perhaps near a different star system. If the wormhole stays stable, stepping into one mouth would allow you to exit the other without crossing the distance between them. So far, that's already extraordinary. But now imagine you take one mouth of the wormhole and move it. You accelerate it to high speed, or place it near a massive object where gravity is strong. In other words, you expose it to time dilation. You make time pass more slowly for that mouth compared to the other. Then, you bring it back. From the outside, the two mouths are still connected in space. The wormhole still links them. But now they are no longer aligned in time. One mouth has experienced less time than the other. That creates a time offset. If you step into the younger mouth, you could emerge from the older mouth at an earlier time, relative to the outside world. In effect, the wormhole becomes not just a bridge across space, but a bridge across time. This is the point where the idea starts to feel dangerous, because once a path exists that connects the present to the past, even slightly, paradox becomes possible. Information could move backward, causes could arrive after effects. The universe would have to tolerate loops, and we don't know if it does. Some physicists argue that nature would prevent this, not through a rule you can read in a textbook, but through instability. Through the idea that the moment a wormhole becomes a true time machine, quantum effects would destroy it, collapse it, flood it with radiation, make it impossible to use. Others point to self-consistency ideas, ways the universe might allow loops, but only if they don't create contradictions. In that view, you could travel back, but you could never change the outcome. Everything you do was always part of the history you're trying to revisit. Either way, the message is the same. If wormholes exist, they aren't a safe, clean doorway to the past. They are a region where our understanding breaks down. Even ignoring paradox, there are physical dangers. A wormhole throat could be unstable. It could collapse during transit. The tidal forces near such extreme curvature could be lethal. Radiation could build up at the mouths. The energy required to create or stabilize one might be so enormous it's effectively impossible. And there is one more hard limit that often gets overlooked. Even in the most optimistic scenario, a wormhole time machine could not send you back before the wormhole itself was created. It doesn't rewrite all of history. It creates a loop starting from a specific point forward. In other words, it wouldn't let you visit the distant past of dinosaurs or ancient civilizations. It would only allow travel into a past that exists after the doorway was built. That limit matters because it shows how constrained these ideas are, even at their wildest. Wormholes are the closest thing physics has to a serious mechanism for backward time travel. They arise naturally from Einstein's equations. They obey the mathematics. And under extreme assumptions, they could create a time offset. But every step toward making them real is blocked by something heavy. Energy requirements, stability, quantum effects, causality. It's as if the universe places warning signs at every entrance. Not impossible, exactly, but dangerous. And yet, the fact that the mathematics allows even this much should leave us with a quiet sense of awe. because it means our deepest physical laws do not completely lock time into a single direction everywhere. Under rare conditions, space-time could twist into structures that blur the boundary between past and future. And if wormholes can loop time, Einstein's equations go one step further. At the very edge of Einstein's theory, time does something almost unthinkable. It curves, then curves again, until it closes in on itself. Physicists call these paths closed time-like curves, or CTCs. The name sounds technical, but the idea is unsettlingly simple. A closed time-like curve is a path through spacetime that eventually returns to its own starting point. Not in space, but in time. Follow the path long enough, and you arrive back at the moment you began. No machine is required, no dashboard, no controls. The loop exists because spacetime itself has taken on a very specific shape. In these solutions, time doesn't just move forward. It bends so deeply that before and after lose their usual meaning. Cause and effect can circle back on themselves. You don't travel to the past. The past comes around to meet you. These ideas aren't inventions of science fiction. They arise naturally in the mathematics of general relativity. Under extreme conditions, very strong curvature, unusual global geometry, the equations allow spacetime to twist into loops. One early example involves a rotating universe. If spacetime itself were spinning in a particular way, the paths objects follow could wrap around in time. Other models involve regions near infinitely dense objects, or configurations so extreme they don't resemble anything we observe today. In these environments, a particle, or even a person, in theory, could follow a trajectory that leads back to their own past. And this is where the consequences become profound. Inside a closed time-like curve, paradox doesn't just appear, it becomes unavoidable. Events can cause themselves. Information can exist without a clear origin. A message could be sent back to ensure it was always sent in the first place. The universe becomes self-referential, not chaotic, not explosive, but circular. Some physicists argue that such loops might be self-consistent, that everything happening inside the loop fits together perfectly, with no contradictions allowed. You don't change the past, you fulfill it. Whatever happens was always part of the loop. But even this idea comes at a cost. If loops exist, then free choice becomes questionable. The path is already closed, the outcome already fixed, the loop tolerates no deviation. And many physicists are deeply uncomfortable with that implication, because while the mathematics allows closed time-like curves, the physical universe seems reluctant to host them. Every known model that permits CTCs relies on conditions that are extreme, unstable, or unrealistic. Infinite rotation, exotic energy, perfect symmetry. Situations where even small disturbances could destroy the structure, and that raises a critical possibility. Maybe the universe allows time loops in theory, but prevents them in practice. This idea was famously articulated by Stephen Hawking, who proposed what he called the chronology protection conjecture. The idea is straightforward. The laws of physics may conspire to protect the timeline. The moment a region of spacetime begins to form a loop, one that would allow travel into the past, quantum effects could intervene. Energy could diverge, instabilities could grow. The structure could collapse before anyone ever enters. Not because time travel is forbidden by a single rule, but because it is incompatible with a stable universe. In this view, spacetime is flexible, but not infinitely tolerant. It can bend, it can stretch, it can even twist under extreme conditions. But when that twisting threatens causality itself, the universe pushes back. This doesn't make CTCs meaningless. They tell us something important about the limits of our theories. They reveal that general relativity, powerful as it is, may not be the final word. That when spacetime is pushed to its extremes, new physics, perhaps quantum gravity, must step in to restore consistency. Closed time-like curves sit precisely at that boundary. They are allowed by equations, but resisted by reality. And that tension matters, because it shows us that time travel to the past is not simply difficult. It may be fundamentally opposed by the way the universe maintains coherence, not by a rule we can see, but but by a balance we don't yet fully understand. At the end of all this, something becomes clear. Physics does not present the past as an open destination. It presents it as a fragile structure, one that breaks easily when disturbed. The future may be uneven, the present may be relative, but the past appears guarded, not by walls, but by consistency. And after all this, the question changes. It's no longer simply, can we? It becomes something far quieter, something far more human. What does it mean to live inside time, if time itself refuses to bend backward for us? We began with something simple, a feeling everyone knows, days passing, moments slipping quietly into memory. From there, we followed time far beyond what it feels like. We watched it slow down with speed. We saw it stretch under gravity. We followed real people who returned from space, having aged differently than the rest of the world. And we traced the outer limits of physics, where equations allow strange possibilities, but reality grows cautious. Along the way, one thing became clear. The universe is not sealed shut. Time is not rigid. The future, at least in small ways, is already open. But the past remains uncertain, not forbidden with warning signs, just protected by consistency. So we return to the question that brought us here. Is time travel possible? The quiet answer is this: yes. In limited, careful ways, the universe already allows it. And no, not in the way stories once promised. But perhaps that was never the most important question. Maybe the deeper question isn't, can we escape time? Maybe it's, how do we live inside it? Because time is not an enemy chasing us forward. It isn't something broken that needs to be fixed. It's the space where meaning happens. Without time, there would be no memory, no growth, no change. Every moment matters precisely because it passes. And tonight, you don't need to solve it. You don't need to understand every equation or possibility. You don't need to travel anywhere else. The universe is vast, but it is not in a hurry. Stars will continue their quiet motion. Space-time will keep unfolding. The future will arrive at its own pace. And here, in this small pocket of the present, nothing is required of you. Just this moment, this pause, this breath. You are not late. You are not missing anything. You are exactly where you need to be. Time is vast, mysterious, and still unfolding. But for now, you are safe inside this moment.